Thank you, Nicola. And first of all, thank you, Laura, Vittoria, for the invitation. I mean, I have really spent a very nice weekend in Vienna, so thank you for that. And yeah, so as you see, the title of the talk is quite vague, and this is because I try to stick really to the title of the workshop. So I'm going to talk about, transport in general in driven systems. So let me start by, again, something very vague and very basic, I think, for this audience. I mean, let's say something general about directed transport. So what I have in mind is situations where you can sustain steady flows. And so if you want to sustain steady flows, you need to put your system out of equilibrium, right? And there are several ways of putting your system out of equilibrium. You can think on putting your system out of equilibrium by applying an external global drive, okay? For instance, if you have a temperature gradient, some sort of pressure gradient and so on, so you will generate, flows, okay? But also you could think of driving your system at a local scale. So you drive, let's say, your constituents individually. So this would be the situation where you can think of your constituents to be self-driven. So this would be active matter, if you want. And then eventually you could mix the two situations, right? And this, I guess, Nicola, you know, is where Pamplona gets most interesting. So, so eventually you have here a bunch of self-driven particles. You have an external field, and by applying this external field, you will generate a flow of active particles, okay, in this direction. So I will discuss the two situations in this talk if I have time. So in the first part, I will show you what I find an interesting, let's say, a scenario of global driven microscopic particles. And in the second part, I will try to mix the two, have self-driven particles under external forcing. Okay, and I think this is in general an interesting question also for soft matter in general, because in principle, by looking at the response of a material, you have access to important material properties. So if, for instance, we want to understand better how an active system flows or how an active solid responds, deforms, breaks, and so on, an easy way to address this question is to apply some forcing. Eventually, the solution of this problem is not that easy, but at least the question is quite natural. So this started quite some time ago by an experimental motivation. So I was going back to Barcelona, and I was looking around the different labs. And then Elena Mazzana, at that time, she was doing her PhD at Pietro Tierno's lab in Barcelona. And she showed me very, very cool movies of an actuated or a driven colloidal magnetic system. So this is the, let's say, a sketch of this experimental setup. So you have a hematite colloids, okay, magnetic colloids. They are heavy, so they sediment. They have a form of an ellipsoid. Hematite is ferromagnetic, so it carries a permanent magnetic moment. And then what they did is to apply a rotating magnetic field in the plane. And so by applying a rotating field in the plane, the particle, if the field is not too fast, will follow the direction of the field. So it will start spin, okay? And so in this way, you can think of it as introducing some sort of chirality in the motion, okay? So all the particles will spin with the same frequency imposed by the external field. So it's an experimental realization, if you want, of a microscopic top, okay? So this is just a sketch. Okay, so what we have in the lab is spinning at low Reynolds number. If you just consider a single top, not much happens, okay? You have your top and it's spinning. But then as the spinning generates a Stokes flow at low Reynolds number, when you have a collection of these colloids, they will self-entrain, okay? You will have a long-range hydrodynamic interactions in between them. So now let's have a look at the situation where you have two of these tops, okay? So you have eventually magnetic, well, dipolar interactions in between your hematite colloids because they carry a magnetic moment. But you can make the approximation of saying, okay, my magnetic moment is turning around at some rate, so I can somehow average the anisotropic dipolar interaction in between them and think of it as an average isotropic attraction. And on the other hand, as your top is spinning, is generating rotational flows around that decay with distance. And so the combination of the two, if you think of it in a very minimalistic way. You have an isotropic attraction due to the dipolar interaction, and you also have a transverse forces due to the flow field they create around. So this is just a time frame of the trajectories of two of these objects. So you see the distance in between them decreases in time, but at the same time they orbit around. And just a movie to see what is going on. You have two of these stubs, they approach, they start generating this orbit, and then eventually they collapse, okay? So now let's put a lot of them together. So the movie is very long, so I'm going to, so they aggregate because of this dipolar interaction. So you see the formation of these drops, and as time goes on, these drops grow in size, and they grow more and more, and this looks like a phase separation, okay? So eventually driven by this average attraction. Now let's have a look, let's make a zoom of one of these big drops. And what you see is that at the boundary, let's say at the interface of this drop, you have a steady flow. Okay, so this is what we call an edge current. Why an edge current? Because in the bulk of these drops, there is no steady flows. Okay, so here inside here, you just have, let's say, vibrations of a quite well-packed configuration of colloids, but all around you have this chiral flow at the edge. So I would like to understand what are the, let's say, minimal ingredients that you need in a system of say, spinning objects to sustain these edge currents, and eventually try to establish a statistical mechanics description of these systems. I'm going to simplify the problem, okay, in a huge way. And here, just to show you that Pietro is not the only one that has made let's say microscopic tops, okay? So other groups have also experimental realizations of these sort of systems. So in this experiment, well, this is basically the same experiment, okay? You also have hematite colloids, they are cubes instead of ellipsoids, but it's basically the same. And in this paper, they characterize very precisely these edge currents, okay? And then more recently, they went to higher densities. And at higher densities, so this is the very same experimental setup as in here, but at much higher densities. And what you see is that the system breaks into some sort of a polycrystal. So here the colors mean the orientation of the local packing. So you see that globally you have a quite a well-packed configuration of colloids, but you have regions of different colors. So meaning that you have, let's say, crystals that have a different orientation. And in between you have these grain boundaries where you have a proliferation of topological defects, and eventually particles, let's say, find easier to move along these domain walls that inside, let's say, the well-packed domain. And also more recently, there are these experiments on starfish embryos where basically you find the same sort of physics, but this is really now driven by the hydrodynamic flows that these embryos generate. So you have hydrodynamic interactions that on one side aggregate these starfish embryos in a water-air interface. They also spin, and this will also generate, let's say, mutual torques in between these particles that eventually generate, let's say, a macrostructure that now rotates as a solid body. Okay, so here you have edge currents, and here you have some sort of a crystal that rotates with a given rate. So all that is just to try to convince you that here, what I think is the key ingredient is the combination of effective attractions to generate drops, let's say, or crystals, and the existence also of transverse forces, okay, of mutual torques. So keeping that in mind, I studied a simplified model, let's say a system of Brownian particles that interact with a Lennard-Jones potential and in the presence of these transverse forces. So if you forget about the transverse forces, it's just a Lennard-Jones system. So why Lennard-Jones? It's just a minimal way of taking into account attraction. And of course, you have a short-range excluded volume interactions. So this is coupled to a thermal bath. And then just to mimic, but really this is a dry system, okay? There is no hydrodynamics here. But just to mimic these spinning colloids, here I add these transverse forces in a way that is, let's say, functional. The way it decays with the space is inspired for, let's say, the far field flow that low Reynolds number a spinning object will generate. So let's put all that into the computer and simulate this system for let's say for low temperatures, okay, where you would expect phase separation. So here I show you movies when you quench the system to low temperatures in equilibrium and for two different values of this transverse force. Okay, so this omega, I didn't mention it before, but it's just that sets the strength of these neutral torques. So what you see is something that again looks like the phase separation kinetics, okay, across phase separation. And what I want you to remember from this movie, because I will go back to it later on, is that the coarsening looks faster when you increase omega. And also, if you want the drop, so let's say the dense domains look smoother. Okay, so if you look compared here and say in equilibrium at these temperatures, let's say Lennard-Jones clusters are very rough, while when you increase these transverse forces, everything looks smoother. For the moment, it's just an observation. So if you, yeah, they phase separate forever until you reach this sort of state. So this is the coarsening, but eventually you need to wait longer. Yeah, okay, it's a full phase separation. So if now you focus on one of these drops, you find again these edge currents. Okay, so the color code is just the amplitude of the tangential component of the velocity. So let's have a look at, let's say, the profile of this velocity field across the drop, across the interface. So this is the same drop, but now when you turn off the transverse interaction. So this is just a Lennard-Jones condensate, and here with a given value of omega. And what you see is that, let's say, in the bulk, so this is the distance to the center of the drop. Particles, let's say, you do not have a net tangent velocity, but then eventually very close to the interface, this tangent velocity increases exponentially. So you can extract from here a typical length of this edge, okay, of the thin layer where particles move. So this interface thickness, let's say this width is this delta, is kind of independent of the amplitude of these transverse forces. And then also an important quantity for the then hydrodynamic description that I'm going to tell you about in a second is to measure also the amplitude, let's say, of the velocity in this edge, and this is something that grows linearly with omega. So if you look at, so I'm just very quickly at an hydrodynamic theory of these chiral fluids, just by, you can think of it as taking Navier-Stokes and adding terms that break a parity symmetry. You must introduce new transport coefficients. And one of these new transport coefficients, there are others, but one of them is what is called the rotational viscosity. And if you look at the hydrodynamic theory, you can predict what should be, for a drop, the width of this edge current and also the velocity of this edge current. And it is independent of omega, and also the velocity of this edge current is proportional with omega. So this is something that you can recover from the simulations of the particle system as well. And also from the measurement of the width of this edge and the velocity at the edge, you can extract eventually this transport coefficient. And if we play this game, I mean, if we apply the results from the hydrodynamic theory, we get this number. But as I mentioned I'm also interested in having, let's say, a more microscopic or stat-mech description of this system. So I would like to define this transport coefficient from, let's say, correlation functions in between positions and forces. So you can do that by computing the stress tensor, let's say, from the Irving-Kirkwood formula. So these are just the forces in between particles correlated with the displacement for the, let's say, two different orthogonal components. And you can define this rotational viscosity as the relation between the shear rate, the shear stress, and the driving. Okay? So if you play this game, you compute this transport coefficient in this way. This is what you obtain. So this dotted line is the value that we got from, let's say, the analysis of these edge currents. And now, if you look at an homogeneous system at the same density as the density of this drop, you would get, from this Irving-Kirkwood calculation, you would get this dotted line here. So I would say that they're close enough. Okay, I mean, it's kind of compatible. Okay, so if you now would like to understand better this phase separation, the first thing one could think of is looking at the equations of state. Okay, so the pressure as a function of density. So we can compute the pressure again by using this Irving-Kirkwood stress tensor if you wanted the virial pressure, so equivalent for the diagonal component. So we compute the pressure as a function of density. You see that these transverse forces do not contribute directly to the pressure because just this scalar product will always be zero because it's orthogonal. But eventually, of course, this spinning, or if you wanted, these neutral torques will affect the collisional statistics. So indirectly, they are affecting the pressure. So these are the equations of state for different values of omega. Okay, so omega 0 is just the Lennard-Jones. And then as you increase omega, you see that, let's say, the typical loops that you would observe in a finite size simulation for a phase coexistence system increase and increase and increase. Okay, so these loops are eventually, if you are in equilibrium, you will interpret these loops as a finite size effect due to the excess free energy coming from the interface. Okay, so if you have a system at the thermodynamic limit, this interface tension eventually does not play any role because it's a surface effect, so you would get something flat in the coexistence region. But for a finite size system, well, you have some interfaces, and so you have an extra, let's say, an excess free energy that is given by the interface tension, okay? And L would be the length of these interfaces. So now if you take this, let's say, thermodynamic idea very seriously, I mean, here eventually we are out of equilibrium, so we are kind of cheating, but let's say that we take that for granted. An interpretation of this increase of let's say, excess area along, let's say, what you would get if you apply a Maxwell construction to get the coexistence region. A way of interpreting this fact is saying, okay, maybe we have an interface tension that is larger or more interfaces. So let's see if we can apply a Maxwell construction and extract from these equations of state the coexistence region. So in order to address this question, the first thing we need to have is some sort of control on the interface length. And so to have a control of the interface length, what we did is to prepare, let's say, drops that now have a flat interface, so this slab, and then look at the pressure across the interface, okay, to try to extract this interfacial tension. So this is an equilibrium. And this, again, is at finite value of omega. And you see, again, that the interface is smoother. Again, it's something going back to these movies at the beginning. And again, you have these edge currents. Okay, this doesn't change. So now what we do is to have to apply some sort of a mechanical definition of your interface tension, but by saying that the interface tension will be the integral of the difference between the transverse and normal, the tangential and normal component of the pressure. Okay? So if you want the integral across, let's say, your slab of the two different diagonal components of your stress tensor. Okay? So this would give us access from the microscopics to a measure of the mechanical interface tension. And these are the profiles that you get for different values of omega. So again, light green is equilibrium, and then darker blue is when you increase the value of omega. So you see that the tangential, let's say, pressure increases when you increase omega. And so eventually, if you integrate with this profile, you will get an interface tension that increases with omega. So if you have self-spinning, let's say some kind of interpretation that I have of this result is that self-spinning is generating these edge currents. This means that eventually you will have more collisions due to these edge currents out at the interface in the, let's say, direction of the interface. So this will make increase of this tangent pressure. This will give you a larger omega. This will give you, eventually, if thermodynamics works, larger loops in the equations of state. And this will also give you, let's say, interfaces that look smoother. Okay, so it looks like equilibrium thermodynamics works, or at least is useful to describe the phenomenology of this system. Okay. So from it, you can construct a sort of a phase diagram. Okay, so this is density, and this is the magnitude of these transverse forces. So here you have this region of, let's say, a gas or let's say a liquid gas phase separation. So this G is for gas and this Cl is for chiral liquid. So along this phase, you have this sort of, let's say, configuration. And you see that there are two different points, let's say, that allow me to put boundaries into this coexistence region. One comes from the analysis of these equations of state if you just apply the Maxwell construction. And the other ones come from the probability distribution of the local density. Okay? And the two of them give you, let's say, compatible results. So again, here thermodynamics seems to allow us to characterize this phase coexistence. And then if you go to higher densities, eventually, and so omega 0 is equilibrium Lennard-Jones. So if you go to higher densities at these low temperatures, eventually you will get a solid phase. So now by increasing omega, you can, let's say, melt or break your solid and get into this sort of state where you have a liquid with a sustained flow. So this is what I'm going to show you in a second. And then this square here represents this phase, okay, where you just have a solid. Now let's start from a solid. Okay, so this is a movie. You start from a Lennard-Jones solid and you start increasing your omega. And this is what you observe, okay? So at the beginning, everything is ordered in the solid, and then you will break it at some point, and you will generate, again, this sort of mosaic of patches of different colors. I mean, this sort of polycrystal that anyway is very dynamic. I mean, if you look at this snapshot from the experiment, you just see, yeah, your patchwork of colors. But eventually, these colors are changing in time because they rotate, and also they break and reform in a quite a dynamical way. Okay, so this is just a snapshot. And here the arrows show you the particle displacement at some typical time scale. Okay, so you see that, of course, where particles find it easier to move is along these domain walls. So now the question, so you see it's quite similar to the experimental snapshot. So now the question that I would like to address for the rest of the talk, I don't know how much time do I have, but hey, okay. Is how to interpret this, how to say it, phase transition, okay? It's very vague. So if you think of this spinning as, let's say, global drive, it looks more similar to, let's say, the yielding of the solid rather than the melting of the solid when you increase fluctuations. Okay, so if you take your Lennard-Jones and you start increasing the temperature, you will melt your solid, but the solid is molten because of the increase of thermal fluctuations. While here is really, I mean, you can think of it as taking your system and shearing it up to some point, which is called the yield stress, above which you break the solid and the stuff starts flowing. The only difference here is that the stress is applied at the level of two particles, not at the level of the boundaries of the system. This is an open question. End of the story. Now I move to the second part. So it is related to this problem, but now let me, just fix again in a very general framework this idea of yielding, okay? So let's change the subject. Now you just have Brownian particles that move because of thermal fluctuations. And I want to, make some sort of summary of jamming and glass transition. Okay? If you have a thermal Brownian particles, eventually by increasing the density, you might end up in a crystal. Okay, for high enough densities, you will have a well-packed configuration. But if by some way you can avoid this crystallization transition, for instance, by introducing some sort of frustration, you can get into a glass phase. So what is a glass phase? Just for the ones that, are not so much familiar with it, is a solid, a disordered one. So there is no, let's say, symmetry breaking in between the liquid and this solid, but things, let's say, particles are arrested. Okay, so you're in a jam phase. And you can achieve this glass also in molecular systems. So instead of playing with density, you play with temperature. And so the glass would be, let's say, a state where your system falls into a state where the relaxation time becomes larger than any accessible time. So your system appears as jammed. And because it hasn't been, fully equilibrated, it evolves out of equilibrium. So if you go back to the first slide, okay, where I was saying, yeah, how to put your system out of equilibrium. You can also put your system out of equilibrium just in a situation where the system is not able to relax to equilibrium by itself. The timescales are so broad that if you look at these timescales, your system will appear as out of equilibrium. This, let's say, glass transition is somehow similar to the jamming transition, which eventually is something different. So by jamming transition, what I mean is that if now you take athermal particles, let's say a bunch of oranges, not Brownian particles, you still have spheres, but they are bigger. So if they are bigger, it means that thermal fluctuations are irrelevant. But still, imagine you have a bunch of oranges, you start compressing the box with oranges, and there is some point where you cannot compress anymore. And if you apply some forces, oranges do not move, okay? Because you have a network of oranges that sustain stresses. So by increasing the packing fraction of your oranges, you can go from something that is able to move if you apply some external drive or doesn't move. So this analogy between jamming and glassy was, let's say, taken seriously by Liu and Nagel already more than 25 years ago. And they proposed this glass jamming phase diagram. What is this glass jamming phase diagram? It's trying to put this physics of jamming and glasses on in the same picture. Let's say, so if you are in this plane here, let's say if you play with temperature, by increasing the temperature, you can go from a glass to a liquid. But now, if you think of the problem at 0 temperature, you are in the world of granular matter, bubbles, big droplets, objects that are macroscopic. And then you can think of an equivalent somehow of a liquid by applying some load, some stresses. And so if you have your bunch of grains and you apply a stress that is large enough, this is what we call the yield stress, then your grains will start flowing, okay? And probably you experience that on the beach. And eventually what they propose is a continuum surface that goes from one plane to the other plane. Why I'm talking about that? Because this picture has appeared recently, let's say, in the biophysics community interested in cell assemblies. Okay, so in this context, also this picture has been, let's say, used, where now what they did is to try to interpret the different, let's say, jamming scenarios, jamming in the sense that cells do not move, that you observe in cell assemblies, but now replacing, let's say, the axis of temperature by the axis of active fluctuations. But these are just cartoons, okay? I mean, as far as I know, there is no quantitative assessment of any of these, a phase diagram of this sort for an active system. So this is what we try to do. We try to take these pictures seriously and try to map this surface in the activity, stress, density, volume. So to do that, I'm going to consider a simple system of active particles. You have these active Brownian particles, okay, and you apply shear. Okay? And now the interactions are soft. These are harmonic spheres. So why do I use our harmonic spheres? Is because in the passive limit, we have a quantitative glass jamming phase diagram. So now what I want to do is to try to understand how this surface, which is the yield stress surface, the stress above which your material starts flowing, is affected by activity. So now in 2 minutes, you look at the flow curves, okay? You compute the stress. From the stress, you can get the shear viscosity. Very quickly, let's say that at low, so different colors are for different packing fractions. So dark, let's say, is very dense, and here is more dilute. So this bold line is, let's say, the glass transition. So you see it here, that is the point at which the viscosity diverges. So below this regime, if you apply a strong shear rate, you have the typical shear thinning. This is in equilibrium, and this is when you have activity, so it doesn't change so much. Just quickly to mention that we also have predictions of what is going on in the linear response regime by some kind of extending Ring-Kubo relations. But let's go back to the jamming phase diagram. So from these plots, you see you can extract a yield stress that would be the value of this plateau in the 0 driving limit. Okay, so by measuring what is, let's say, the high of this plateau in the stress profiles, you get this surface. So again, now here you have the yield stress, here you have the packing fraction, and this Peclet number is the way of quantifying self-propulsion. So if you don't apply any shear, you find this line, which is the active glass transition. So if you are inside this surface, your system is arrested. You're in an amorphous active solid. But then you can break it by applying a stress. And just very quickly, just the question here is whether we can interpret activity as some sort of effective temperature, because eventually this is very different than, let's say, the Liu-Nagel phase diagram, because active fluctuations are out of equilibrium. And here, just very briefly, these are, let's say, the yield stress curves as a function of the packing fraction for different Peclet numbers and different temperatures, because we want to compare the effect of one with respect to the other. So eventually, as a temperature increases, you push the glass transition to higher packing fractions, also with activity. So in this respect, is as, let's say, harder to sustain a glass. But then as you increase the temperature, the yield stress increases, while when you increase the Peclet number, you are pushing your curves towards the jamming limit. Okay, so it has an effect that is quite different, because you shift the curves towards the thermal limit. So this is just to conclude, but just one thing quickly. This is a call for the experimentalists in the audience. So there was quite some effort, let's say, by the colloidal soft matter community to quantify these, let's say, flow curves, really the rheology of emulsions, foams, colloidal suspensions, and so on. So now you have to do the same with active systems. It would be nice to have some quantitative assessment of whether, let's say, jamming or arrested state towards the flowing state that we observe in active systems is more glassy-like or jamming-like. And with that, since I'm running out of time, just to thank my collaborators, in particular Claudio, who is the one who did all these simulations of the chiral spinning liquids, and Roland, who was the one who carried on the simulations of the active particles under shear. And with that, thank you for your attention. Yeah. No, these are spheres with let's say springs. Yeah. Well, I imposed a linear profile of velocity. Because I had this phase diagram in mind. Because they use the same protocol, and as far as I know, is the only quantitative glass jamming phase diagram around. Yes. Yeah. Yeah. We have to do that. Yeah. Yeah. Yes. It's not. Yeah, it's not. I mean, in the simulations, the only ingredient there is that the interactions are like that. They exert torques, and you have attraction. So the magnetic component is taken into account in a very effective and minimalistic way by the Lennard-Jones potential. But we are not resolving, let's say, the dipolar moment. Yes. Yes, I did. And I didn't manage. But I did. I tried. But I'm going to try harder. Yeah. Because also there are all these issues on the odd viscosity and so on, and to really the But yeah, we are thinking about moving to 3D. But yeah, I mean, there are also these questions. I mean, there are other transport coefficients that appear also at the hydrodynamic level that for the moment here we don't have, yeah, consistent access to it, or at least conclusive access to it. But for that, we will need capillary wave theory. Sure.